The ambition of a general-purpose robot that can truly understand and interact with our world is no longer just science fiction. We're moving beyond simple, repetitive tasks. The real challenge? Teaching robots to handle complex, multi-step chores that require reasoning and dexterity. Today, we're diving deep into Google DeepMind's groundbreaking Gemini Robotics, a system designed not just to follow commands, but to reason, plan, and act in the physical world. So what exactly is Gemini Robotics? It's the latest generation of robot foundation models from Google, engineered to be the core intelligence for general-purpose physical agents. The goal here is to empower robots to perceive, think, plan, and execute, even using tools to solve novel problems in the real world. The architecture is a brilliant two-part system. First, you have Gemini Robotics-ER 1.5, the Orchestrator. Think of it as the high-level brain. Its specialty is embodied reasoning. It understands the physical world, formulates complex plans, and can even query Google search for information. It's already setting new state-of-the-art performance across 15 academic benchmarks. Second is Gemini Robotics 1.5, the Action Model. This is a powerful Vision Language Action Model, or VLA model. It takes the high-level plans from the orchestrator and translates them into the precise low-level motor commands the robot executes. Its killer feature is a motion transfer mechanism, allowing skills to be generalized across different robot platforms without retraining. The system's power comes from four key features. First, its agentic capabilities. The two models collaborate, allowing the robot to reason and use tools proactively. Second, embodied thinking. The models generate an inner monologue in natural language to break down tasks, which is huge for robustness and interpretability. Third is generalization. Training on diverse robot data allows skills to transfer to new tasks and environments. And finally, excels at handling complex, multi-step tasks. The exact kind of daily chores that have been a major barrier for robotics until now. And the use cases demonstrate this power in action. Imagine a robot packing your suitcase by checking your travel itinerary and the weather forecast online. Or one that can perform a web search for a risotto recipe, then find and gather all the ingredients. We've seen it sort items for a user with a specific nut allergy by researching safe foods first, and even perfectly reorganize a desk by memorizing the initial state of all objects. Let's look under the hood. The workflow is an elegant agentic loop. The orchestrator, ER 1.5, receives a high-level command. It uses its embodied reasoning to decompose it into a sequence of simpler steps, using tools like search if needed. Each step is then passed to the action model, ER 1.5. This model uses embodied thinking to generate its own text-based thought process, breaking the instruction down even further, before translating it into the final motor commands for the robot. From a performance perspective, the data is compelling in long-horizon tasks requiring planning and tool use. The full agentic system significantly outperformed baselines, including powerful off-the-shelf BLM models. This proves that the specialized embodied reasoning of ER 1.5 is critical. In fact, on an aggregate of 15 academic embodied reasoning benchmarks, ER 1.5 established a new state-of-the-art, outperforming models like Gemini 2.5 Pro and GPT-5. Furthermore, its thinking mode and motion transfer were validated in ablation studies to be crucial for its success and generalization. For all the developers and architects watching, here's the access breakdown. The orchestrator model ER 1.5 is available right now via the Gemini API in the Google AI Studio. However, the action model, the VLA, is currently restricted to select partners. So at present, there's no publicly open source or local version available for the full agentic system. Of course, we need to address the limitations. The system's raw dexterity hasn't seen a generational leap. There's still a 22% total failure rate on long horizon tasks, stemming from planning, perception, and action failures. And the motion transfer, while powerful, is less effective when the embodiment gap between robots like a robotic arm and a full humanoid is very large. So what's next? The team is focused on solving the data scarcity problem. By using human and synthetic videos as new training sources, they're also exploring new architectures and reinforcement learning to boost dexterity and physical capabilities without sacrificing that all-important generality. This is a foundational step towards solving AGI in the physical world. What task would you give a general-purpose robot? Drop your ideas in the comments below, and don't forget to like and subscribe for more on the future of AI in robot.